Okay, so now we have the last talk of today's session. So our speaker is Santanu Das, and he will be talking about a unified law of robustness for Bridgman divergence losses.
Yeah, so thanks for the introduction. I'm Shantanu. I'll be speaking on this unified law of robustness for Bridgman divergence losses. And this is a joint work done with Jatin Dutta and Piyush Srivastava. So often what happens whenever a data set is given to a statistician and the statistician has to yeah, the statistician has to choose a model for the data set. Then when statistician always in a bit of tension because the model should be powerful enough so that it will capture the structure in the data. But at the same time, the model should not be that much of powerful so that it will interpolate for the noise also. So he has to balance the both of the thing and he has to make a wise choice for the model. So now how can you define the what is a power? How does it quantify the powerfulness of a model? So in simple language, you can say that so if a model has so many number of the parameters, then the model is powerful. Otherwise, if a model is a less number of the parameters, the model is not that powerful. Is less powerful. So so going in this direction, there are two lines the code set by the yes. Yeah, said by the von Neumann and the quoted by the Enrico Fermi, and it is saying that with the 4 parameter you can fit an elephant, and with the 5 parameter you can make the elephant to rebel his trunk actually. So that jokes apart, that's the powerful one parameterization is. You can do anything with the data. You can fit anything if you increase the number of the parameters in the model. So now let's formalize this setting. So let's assume the data set is given to a learner, endpoints are there, and a function class is also given to the learner. Now the learner has to choose a function that either interpolates the data or fits the data below a particular noise level. So this problem is called the data memorization problem. And in this talk, I am going to address the following problem: how many parameters are needed to learn a robust array? So now what is robustness and why the robustness is required and how to quantify it? I am going to address these questions in the following slides. So first of all, why is robustness is required? This is because the neural this is because the neural networks are very vulnerable to the adversarial examples, and the most serious examples are the ones when you are given to the neural network, when you perturb just one coordinate of the input or one coordinate of the data that you're giving to the that you're giving for the training set. And what do you want? We want and we want the performance of this neural network should be stable according to this kind of perturbation. Or we can say that in order to get rid of this kind of problem, we want our model should be robust. And how does it define the robustness of an estimator? So an estimator is said to be robust if the output of the estimator does not change much when we change the input of the estimator a little bit, or a little bit perturbation is given to the input, but the output does not change very much. That is the definition of robustness of an estimator. Now the point is, how do you quantify the robustness of an estimator? So there are several ways in which we can quantify the robustness of an estimator, but throughout this talk, we will opt this measure of robustness called the Lipschitz function of the estimator. Now we know that a function is said to be Lipschitz if there exists a L such that f of x minus f difference between f of x minus f of y is less than into L times of distance of x and y. Now we can see that if your L is too high, then even a small perturbation to the input, the output can change output can change drastically. But if your L is small, then given a small perturbation to the input, the output won't change. And this is evident from the definition of the Lipschitz function. So we are saying that if L is high, then our model is non-robust, and if L is small, then our model is robust. So we are quantifying the robustness of an estimator using the Lipschitz function. Now in the next 2-3 slides, I'm going to take in some data sets, and I'm explicitly showing you how to fit in them, how I'm going to fit them, and I am saying that how many parameters I am going to use, and I am also saying that what is Lipschitz constant of a particular city. Let's go with the first example. So here I have taken n data points. So if the xi is the sample from the uniformly from a surface of a dimensional sphere, and the yi is sampled from a Bernoulli distribution with probability with probability half and supported on -1 and 1. So this kind of data set are called the generic data sets. Now our class of function is fixed. It is a one hidden layer of neural networks. And now what we want to do? We want to take a function from this class. We want to fit our data set. So what we do? We just first we plot all those points on the surface of the sphere, and after that we make the small caps. Small cap means this definition. We will just take all those points on the surface of the sphere which are highly aligned to the x side, and we make the small caps. And and we know that, we can show that these caps are always disjoint. So there is nothing intersection with high probability. You can show that these caps are always disjoint. And how can you show? How can you prove that? There is a simple, there is a simple proof is there. You first just define this event P. So event P is saying that there exists a J which is not equal to I, such that exogenous product X is greater than 0.95. Then you can just show that probability of P is less than equal to something n into to the power minus 0.95 equal to H. And I am assuming that D is high enough so that this n D this probability is very small. So now we can show that this function is f(x) summation equal to q equal to n. Sorry, there will be one yi. So function f of x equal to summation k equal to 1 to n yi into 20 into value of x dot x inner product minus 0.95. This fits the function completely. ReLU is ReLU is 0, ReLU of x equal to maximum of 0, x. So you can show that this fits the data completely. Now you can see that Lipschitz constant of this function is 20, and the number of the parameter that we are using, that is we are using one neuron for the each point. So there are n point, number of the parameter is n times d. So the number of the parameter is very high actually, right? It is n times d, where n and d are both high, and the Lipschitz constant is constant type of Lipschitz constant. So it is a you can or in my words it is small Lipschitz constant, and number of the parameter is very high. Let's see one more example. Here I am taking the same generic data sets here also, but I am just fitting the linear functions here. But here n equal to d, n equal to d, and I am just trying to find one linear predictor such that w dot xi equals to yi. So Lipschitz constant will be norm of w square. Now I am taking that one that minimizes the norm, and that w x transpose inverse equal to y. And you can calculate Lipschitz constant that will be root over y transpose x transpose inverse y. And we can show that for generic data with high probability this will be identical, the x transpose will be identity. So the Lipschitz constant will be order of root d. But see that here we only have d number of points, but the Lipschitz constant is very high. It is root d. So so summarizing these two examples, we can say that we have bigger models tends to more smoother than the smaller models. Bigger models, I mean, now number of parameters is much higher actually. So bigger model tend to be more smoother, or you can say more robust compared to the smaller ones. So this was originally conjectured by the Vivek Lee and the Nagaraj in their paper 2021, where they are saying that if you have generic data sets and and if your class of functions are the one hidden layer neural network with ReLU activation function, such that your hidden layer consists the k neurons, then you can say that with high probability of sampling of the data, if there exists a function from this class that fits the data completely, then the Lipschitz constant of that function should be greater than root n d by p. Here p is exactly k into d plus 1. So this was the conjecture made by the Vivek Lee Nagar. That's why people see that these data are the generic data set. Class of function is so simple, but in general, when we usually fit the data, then data that are not generic and the class of function is not one hidden neural network. So
what does P represent?
P number of the parameters. Number of the parameters in the neural network, that is k into d plus 1. So I am going, so the main concern is this the general relationship between the number of the parameters and the robustness of the estimator. So in this talk, I am going to convince you that this is the indeed the general trend followed in a wide variety of the settings, in a wide variety of the situations. Yeah.
So in Quebec, they are Nagaras, they prove it for.
No, they have just made the conjecture, they have not proved it.
No, but they have some result.
Yeah, they have
And
some.
that is not the square.
No, that is only Bubec and Silke, that is not Bubec and Nagaraj. Yeah. So we will begin with the first result in this setting, and this was given by the Bubec and Silke in 2021 itself. And this result states that, okay, now if be a class of functions from RDQ minus 1 to 1, you have input output data pairs are there. Now there are three assumptions are there. First assumption states that if admits a Lipschitz parameterization by P real parameter, each of size is at most polyhedral. Second is saying that the distribution of on the covariate satisfies isoperimetry, and third one is saying that the expected conditional variance of the output is strictly positive. Just don't worry, I'm going to explain all these assumptions in the later slides. What these assumptions mean actually. Now, if you take some more concept on the A and B, then you can say that with high probability over the sampling of the data, if any function which fits the data below a particular noise level, then the Lipschitz constant of the function should be greater than root ND by P. So these are the results given by the Bubec and Silke. Now, let's see what these assumptions means actually. What is the so the second assumption is nothing but the form of subversion measure should hold. That's it. The first assumption means that you have a bounded subspace in R3. From there, you have a Lipschitz map which is mapping to your function space. This is the first assumption. So this is the meaning of the first assumption. And this first assumption also concludes that you can have a epsilon net covering for the function class. So if you are looking any kind of property data depending on the distance kind of thing, then you just need to that green points, and you don't need to look the whole function class. Just looking at the green point will do the job actually. And this property is also allowed to do some tweaks in the proof also, will help in the proofs also. The second property is saying that every Lipschitz function concentrates with respect to the measured mean, and this is satisfying this kind of sub-Gaussian concentration. This is the meaning of the second assumption. And the third assumption is that the optimal the expected value of the expected conditional variance is the optimal predictor. That should be this noise should be greater than 0. This should not be equal to 0. So these are the three conditions. Now note that this is applied for the square loss and this is for the regression task. Now I'm coming with our result. So Bubec and Silke have shown the law of robustness, their theorem for the square loss. But the square loss is well suited for the regression task. But what about the other tasks? Like when you use the logistic loss for the binary classification or the cross entropy loss for the multi-class classification. What about them? And so is the law of robustness truly robust to the type of the loss function employed? So if you change the loss function, you change the task. If the loss function is the law of robustness remains same. So that is where we enter into the picture. So now we can see that this all kind of loss, square loss, cross entropy loss or logistic loss, these all kind of loss will come under one common class of loss function named as the Bregman divergence loss. So what is Bregman divergence loss? So let's see phi be a function from omega to where it is strictly convex continuously differentiable function defined on a set where omega is a convex set, and the Bregman divergence between 2 points is defined as this. So it is a kind of a distance measure. It is a kind of distance between 2 points, but it is not actually the distance. And as I said previously, your square loss, cross entropy loss, these will be examples of the particular kind of loss. Now this is our result. So if I denote the Bregman divergence loss, delta be a subset of RD, omega is a subset of RK. You have a class of function from delta to omega. Your xi and yi will be the input IID pairs for the delta and omega. Now see that the first two assumptions remain same. Only the third assumption change here. Third assumption, the expected loss of the best possible predictor for the Bregman divergence loss is strictly positive, and that you defined as sigma square p. So it is the So you first take the expectation of dphi comma fx for all f or possible f. You minimize that, and yeah, you minimize it over all f, and the minimum value sigma square phi. Now you can see that if you take the if you define the square law, then your sigma square is equal to just the sigma square as the previous case. If your dphi is a cross entropy loss, then your sigma square phi will be the conditional entropy. So it will change depending on the Bregman divergence you are choosing here. Then if your n greater than this k square r by epsilon square, then similar to that, with a high probability over the sampling of the data, one can be shown that if there is a function which fits the data below a particular noise level, then the Lipschitz constant will be greater than this root n d by p, and 1 by order of root n d by p given 1 by k. So similar kind of result, but note that here is the task is not defined. Task can be anything. It can be regression, classification, anything, and you can choose your dphi according to your task. But the point is that dphi should be Bregman divergence kind of form. Yeah. So this summation I equal to 1 to n 1 by n dphi y comma f of x I less than equal to sigma square p minus epsilon. This is the self of overfitting that I am saying before, data memorization. Yeah, so the main conceptual contribution, our main conceptual contribution here. So the expected, we know that the conditional variance serves as the optimal predictor for estimating y based on x for minimizing the square loss. And this will give a bias variance type of decomposition of the square loss. And yeah, and our main contribution is to observe that this basic fact lies at the heart of the proof of the Vibekan cell case. But we are talking about the Bregman divergence law. So we have found out that this is not only true for the square laws, but this is true for the Bregman divergence losses also. That E of y given x is the optimal predictor when estimating y based on x when minimizing any kind of Bregman divergence law of the type dphi y comma x. So this is true for the Bregman divergence type of losses also. And using the triangle equality, for fixing the z equal to u y comma x, we can get a bias variance type of decomposition for the Bregman divergence losses also. Yeah. Yeah, we show that this using this simple but important fact is Dubrow-Selkev analysis could be generalized to all the Bregman divergence loss using just these two facts. And the rest of the technicalities depend on the standard concentration peak and the epsilon net argument. Thank you. Thank you.
Questions?
Also, like, do you assume anything on this function either?
Yeah, there are the other technical conditions are also involved, which you need to solve this problem actually.
I mean, do you assume that strong on this?
No, not the strong, only conflict is sufficient.
Okay, so if there are no more questions, let's thank the speaker much.
Let's also thank the three chairs, Madhar, Viswanatha, and Pranav. And for those of you who want the tactical experience, just send an email to me and send out the speaker. Thank you. We'll meet here at 9:30. Breakfast will be at 9 tomorrow.
It's.